Hello everyone. So in this lecture we are going to discuss another method of synthetic graphite production or artificial graphite production, and this type of graphite is known as Kish graphite. Okay. Now I'm not 100% sure if it's pronounced Kish or Kish. Because this is I know that this word is taken from a German word which is keys, and keys basically means all the impurities like dust particles and stone and things like that which are mixed with your food grains. Now the term was borrowed because of the fact that this is sort of the waste material from your steel manufacturing industry. So what would come out as the waste of steel manufacturing? You have iron, you have carbon, and you also have some other minor quantities of other elements depending upon the exact composition of your steel. Now when you mix all of these elements and when you rapidly cool this entire mixture down, then what happens is the excess elements, excess amount of iron, excess carbon or other elements, all of this, whatever did not participate in steel making, it precipitates out and it deposits on top of the surface of your ingot that you're making. So from that waste material, we collect that waste or the film of that waste that gets deposited, and then we extract graphite from it. Okay, so how will you do that? Typically, you will use methods which are rather similar to what you do for graphite ores. So you will do initially some sieving or some basic filtration methods, but after that the primary method would still be flotation. So you remember the froth flotation methods. This always works for graphite because graphite is hydrophobic and it's also light material, so it can easily float. And often the other impurities are more like heavy metal impurities and salts and so on. So they are either hydrophilic or they are heavier, so they get precipitated. So we'll do flotation, and then of course afterwards we can also do milling. We can also do a little bit of milling or powdering of the mixture beforehand, and so on. And then we'll also do magnetic separation, because this material came out of iron, right? It was a steel making byproduct, so it will have certain iron, but that is very easy to remove, because you can always do magnetic separation to get rid of your iron. By doing this, you can actually get up to 99% purity of your graphite. And this graphite is in the form of flakes. In fact, it is similar to the flake graphite that you get naturally. And sometimes in the literature, you might also find the word flake graphite, which is used for this kind of material. Okay. Now, how does it grow? So I have shown it here in this picture. You have nucleation of certain dendrites, and then dendrites means these are like these crystal structures which grow in 2 dimensions. So flakes, most of the flakes they grow in this form. So you will have nucleation and then growth of your dendrites, and then at some point these dendrites grow so much that they sort of overlap each other, and then you will have a complete film. So this is basically similar to any thin film formation. Often you will have this nucleation and growth, and then the complete area is covered. So this is how the graphite flakes grow on top of the surface of steel. Now, as I mentioned that when you cool the graphite, cool the alloy, only then you get this graphite film. So by controlling the cooling rate, you can have slightly thicker graphite flakes, but in that case you may have the spread, the dendrites may not be long, or you can have, it depends, you can choose the conditions. So you can have either long but thin flakes or short but thick. So thick when you want, what do you want when you want larger LC? What is LC? LC is your is the stack thickness. So if that is more important for your application, in that case you would slightly choose the condition accordingly. But remember that this is a byproduct of steel manufacturing. So you do not always do the process according to the graphite that you're getting. You will rather do it depending upon what you want to get from what kind of steel do you want. So you may not have the control over all the parameters, but these are the conditions that will give you different types of Kish graphite. Okay, now you will have this, you can, of course, for various applications that this can be used. Now you can use it also directly as flakes. So the flakes are typically, you know, 0.01 to 0.1 millimeter size. They can also be larger though. That again, as I mentioned, that depends on how you're preparing it, but you can have, you know, reasonable flake size and also reasonable flake thickness. So depending upon your application, you can then post process it and then use it. Okay. Now, what is the mechanism of the formation of this? Why do we have, what happens? Why do we get this graphite out of it? So if you think about it, you have carbon particles which are distributed throughout your alloy. They are sort of, let's assume that they are uniformly distributed inside your steel alloy, and now there is a sudden quenching, sudden cooling. In that case, they just all want to go out. However, now on top of the surface of your steel, you have a lot of carbon atoms, millions of carbon atoms, and they do have the energy that is required. So they very suddenly, they form a material, a carbon material. What is interesting is that this carbon material could have been anything. Why graphite? Graphite, because graphite is the most stable form of carbon. So whenever you have atomic forms of atomically deposited carbon, and you also have these very sudden cooling conditions and so on, it will try to go into its most stable, the carbon will try to go into its most stable form, that is graphite. Okay, now in terms of the phase diagram, we discussed the phase diagram of elemental carbon. So for us, what was more important was graphite and diamond phases, and we did not discuss so much about the solidus and liquidus lines. But if you have learnt the iron carbon phase diagram before, you know that liquidus line is the line that is between the solid plus liquid state and the completely liquid state. Okay, so basically above this line, your material will, or element or alloy will always be liquid. However, as soon as you go below the liquidus line, that means now some solid may also exist along with the liquid. And that is when you have the Kish graphite forming. So whenever your cooling is done below the liquidus line and the solid particles start to precipitate and coexist with the liquid, that is the time when you get these graphite flake formation. Okay. Yeah, so this is an atomic deposition, although it is a very large surface, but it is a very sudden and atomic, atom by atom deposition of carbon. Okay, and also this is layer by layer, and since we have these very sudden changes, that is why we get graphite, the most stable form. Okay, now this we already learned that we have a nucleation, growth, and spread of the crystal structure, but in a very rapid manner. You can use this material directly, or you can then pulverize it and so on, and then use it for various applications. Basically, this is all about the Kish graphite. The good thing about this material is that we get it from the waste. So it is graphite, it is crystalline, it is actually similar to the flake graphite that you can find naturally. However, this is because we extract it from the waste, it's relatively inexpensive, and it has a reasonable crystal size and crystal structure, so it is usable for a lot of applications. It also has a very high purity. Okay, so the third method of graphite production is the heat treatment of polymers. So in the first method was heat treatment of petrochemical products such as coke and pitch. Now this is the third one. Now the heat treatment of polymers is done for making a lot of carbon materials, not just graphite. In fact, it is rather used more for making what is known as non-graphitizing carbons, and then there are fewer polymers, however, that will also give you some graphite. At some point I must have mentioned it to you that interestingly, when people were actually trying to prepare graphite from the polymers, they ended up making other types of carbons. So what happened was, in the 1940s and 50s, graphite became very important for, for example, for nuclear reactor applications and batteries and so on. And at that time, people did not use other forms of carbon. They rather, preferred to use graphite. So it was needed in very large quantities, and then people ended up trying out different things. One of them was to convert polymers into carbon. Now people initially thought that anything when it is heated to up to 3000 degrees, then it will convert into graphite. So that was initial impression. People always thought that, okay, maybe at 1000, 2000 we still get some sort of disorder in the material, but the material will continue to get more and more and more order, which sounds obvious, right? That it will get more order, because if you keep on heating it, at some point before its sublimation temperature, which is about 3500, before that it should convert into graphite completely. But it turns out that that does not happen. In fact, there are certain types of carbon materials, no matter how high you will heat them, they do not convert into graphite. So they never have this anisotropic crystal structure, never have the layers of single layers properly arranged in ABABA fashion. Okay, we will learn about those materials, non-graphitizing carbons, in our next couple of sections, but now we'll talk about graphite. So not all polymers give you graphite. As I mentioned, you should have certain anisotropy which helps. Or what you can also have is that you have an aromatic backbone, but this may not always work. What aromatic backbone means, you have aromatic structures, so ring-like structures. And backbone of a polymer means this is the primary structure of the polymer. On the sides you can have something else, but this is the sort of the backbone, that is what is called the primary structure of the polymer. So if you have that, which is aromatic means you have already these 6-membered rings, but you, of course, when it's a polymer, you have hydrogen, it's CH. And what you want is, you want to get rid of the H, all of the hydrogen, and of course all other elements as well. And then what you get is, however, then it is more already, since it was in the ring-like geometry, you will get these kind of the graphitic regions. But graphitic does not mean it is graphite. When we say graphite, that means you need to have 3D structures, and also at larger scale it should not be a disordered carbon, it should be more of a polycrystalline graphite. So for that purpose, very few, extremely few polymers can be used. Okay, so yeah, and you should have high carbon content. That is a very general thing to say, because even though you have a high carbon content, that does not really determine the crystal structure. It just determines whether or not you will get carbon, or carbon at all. Because some polymer molecules, for example, they contain a lot of oxygen. So the polymer chain itself contains a lot of oxygen. You have some CO bonds and so on. Now what will happen? You keep it in the furnace. You keep it under the inert atmosphere, so you have nitrogen or argon flowing inside your furnace. However, the polymer itself contains so much oxygen that it will burn. It will get oxidized, or if not all of it, a lot of it. So what you get at the end, you will get just a little bit of powder of the carbon, but a lot of mass loss will take place, and that is what you don't want. Also, there are certain other elements, for example, chlorine, and any oxidizing materials you typically don't want in your polymers. But again, there are no hard and fast rules, and sometimes you need to just try things out. Especially nowadays, you have a lot of new polymers in the market. And there is actually a lot of research in the field of polymer chemistry. So when you have any new material, you can guess whether or not if it is not a carbon backbone polymer. For example, if you have PDMS, which is mainly a silicon backbone, silicon based polymer, in that case you can already say that there is very little possibility that this will give me any carbon. And even if it does give me very small fraction of carbon, definitely the shape that I have made, that will be lost. I will just get some residual carbon. But in the case of some polymers, you can say that I'll get some polymer, some carbon, but whether or not it will be graphite, that is hard to say without any experiments. But in principle, if your polymer is already semi-crystalline, semi-crystalline means it already has some layered arrangement, and if it has reasonably high aromatic content, then you might be lucky and you might get graphite out of it. Okay. Yeah, so all these things I've already mentioned. This polymer known as polyvinyl chloride or PVC, you must have heard this polymer is used for for making a lot of things. For example, the plastic pipes that you see for agricultural purposes, or for in any tubes. You see these plastic pipes, gray colored, they are PVC pipes. And there are also a lot of composite materials that utilize PVC. You have various elastomers, even rubber-like structures also. Sometimes they are based on PVC. So there are a lot of PVC. Even there is carbon reinforced PVC that you have in car seats and so on. So there are a lot of applications of this polymer. And this polymer is actually a graphitizing polymer, which means this polymer gives you a carbon material which is graphitizable or graphitizing, which means it can be converted to graphite when you go to very high temperatures, unlike some polymers which will, even at 3000 degrees, will only give you non-graphitizing carbon. So in this on this slide now, I have a few structures of chemical structures of polymers. For example, also anthracene will give you graphite on heat treatment. But then there are also some other structures that I have drawn here. For example, a phenol formaldehyde resin or a furan resin. We will discuss these materials, especially the polymers which will give you non-graphitizing carbon, that we will discuss in the next section. Pan or polyacrylonitrile is actually a polymer which is used for making carbon fibers. And this typically gives you non-graphitizing carbon. However, under extreme conditions, under 3000 degrees and very thin fibers and so on, it has also been reported to provide graphite crystallites. Okay, so but what we do for fibers, again, we'll talk about that in the fiber section. Cellulose gives you non-graphitizing carbon. Cellulose means, well, if you take piece of wood that contains a lot of cellulose. So you can actually try to put it in a furnace under inert atmosphere, and what you will get will not be graphite. Okay. Yeah, so now let's just briefly discuss how do we do this heat treatment. You will generally have what is known as a tube furnace. So there are different types of furnaces. Now, furnace is anything where you can heat something. Now there are variations called muffle furnace, and there's chamber furnace and tube. So you want to use the tube furnace, which, as the name suggests, contains a tube. That tube might be either made of ceramic, alumina, for example, or it is typically it's made also of quartz glass. Depends on how high you want to go, what is the temperature that you want to use. So quartz will typically not survive above 1200 degrees. Even depending upon the quality and the defects, it might even melt slightly earlier than that, but up to 1200 typically it survives. But if you want to use a very high temperature furnace, for example, you want to go up to 1600 degrees. Or in the case of graphitization, typically you want to go to 3000 degrees. Then you will use ceramics. Initially up to 1600, up to 2000 degrees, typically alumina, and above that you might also consider using silicon carbide. In extreme cases, you might even use the rod, the tube that is made of a certain type of carbon material. Then it can really withstand very high temperatures. So there is a tube, and very basic, simple principle is that it's a tube furnace, and you want to maintain an inert atmosphere. So what will you do? You will have a nitrogen inlet and outlet. Nitrogen or any other inert gas. Nitrogen is used for most of the lab research purposes because it's relatively cheaper and easily available. But you can also use argon, helium. You can use other gases as well, other inert gases. Okay, so under the nitrogen flow, then you have your polymer slowly heating. Slowly is important also because when your material is heating, now I'm going to explain to you, when your polymer is heating, you have certain bond breaking reactions, and after that certain bond forming reactions, and you need to sort of allow enough time for these reactions to properly take place. And you want to reduce the loss of your carbon material as well, because you will lose some carbon in this process. It's not like only the non-carbon atoms will go. They will take some carbon away with them as well, which you want to minimize. So, okay, here in this schematic, I've only shown you the tube, not the entire furnace, or not the heating coil, and not the glass wool. And you'll typically have some certain thermal insulation in your furnace, so that because you are using really high temperatures, you are using 1200 in the case of graphite, up to 3000, so you don't want to touch it. So you will have good thermal insulation so that the surface temperature is always maintained below 150, typically 100. Below 100 is good. So this is the schematic. Now you see in that little sample holder, I say carbon. So this was not initially carbon, this was a polymer. And now this polymer lost some of these when it was heated. Then some of the non-carbon atoms were removed. How? Oxygen took some carbon with it. So some oxygen was there, let's say. Now that took some carbon with it and formed carbon dioxide and carbon monoxide and left. What happened to hydrogen? Hydrogen also formed, it took some carbon with it, formed methane and left. Now there may be also certain, during the initial stages, you also had the polymer fragmented into smaller polymer molecules, so smaller fragments, smaller hydrocarbons. They were, if they were too volatile, they also left without completely degrading. This, if they were too volatile, they also left. Now what you're left with is heavy hydrocarbons, something that is not so volatile that it can just mix into your nitrogen and go away. But it's also not, it's like this oily, tarry material. So it's also not going to form be a part of your solid carbon material. It is volatile enough that at 1200 degrees, let's say, it will be removed from your solid material. But then it's also not going away. Often it gets deposited onto the walls of your furnace. You will see some tarry deposits. Now, of course, when you're doing this process at a large scale, then you can also collect these tarry deposits separately. So again, this is a very, very, very fundamental schematic. Industrially, you will have a lot of different pipes connected to it, from where you are, for example, constantly removing your tar and constantly removing these gaseous hydrocarbons that are coming out of it. And then the heating and cooling and everything is very well controlled. Also, cooling is controlled in the case of industrial processes. So this is the fundamental thing. The third thing that you have after everything is left, then what you have is the solid carbon material that will be, that will be maybe 30% of your original material. That depends on the mass loss. That depends on the chemical structure of your polymer. Okay, so different. This is again, I have already mentioned. In the case of graphitization, or when you want to make graphite, you will for bigger sizes, or then you will use above 2500 degrees, typically 3000 degrees temperature to get good graphite. And of course, if the sample size is very small, or you have a very thin film, in that case you may use lower temperatures, because then you're providing a lot of surface area for these stars and gases to be removed, and that is why you can use slightly lower temperatures. But if you can use 3000, then you will most likely do so. Okay. Now, yeah, these also the fact that we are using a tube furnace. I didn't tell you. The fact that we want to, all these the tars and the synthetic gas that is being produced. Synthetic gas is the mixture of all of these, the gaseous hydrocarbons. Now, all of these things, when they are produced, as soon as they are produced, they should be removed. So they should be pushed, and that is why we have the tube. If you have a chamber furnace or something where these things can circulate, they may end up redepositing on top of your sample, and you want to avoid that. So that is why you need the tube furnace. Okay. Yeah, and this process is done slowly in order to provide. So 1 to 10 degrees centigrade per minute is the temperature increase. The slower the better. And also, once you reach this highest temperature, let's say for your process it was 3000 degrees, you will leave your material at 3000 for a while. So at some point we'll also learn this entire process it's a combination of both thermodynamics and kinetics. Thermodynamics in the sense that you have various reactions. Every reaction has a different energy. So why I'm saying various reactions, because when your polymers are broken into smaller hydrocarbons, now each hydrocarbon also might be breaking into further smaller hydrocarbons. Or there is also this one reaction going on where you have carbon radicals which are attaching with each other and forming a solid carbon material. So it's a very, very, very complex mixture at any given temperature point. let's say at 500 degrees, if I look at that material, it has so many reactions and so many different aspects of it that you cannot really, it's really difficult to, let's say, if you want to model it. So this is very difficult. However, all of these reactions have their own, Gibbs free energy. They have their own, whether or not they are thermodynamically possible. So that you need to calculate for every individual reaction. Also, at the same time, you need to see how long, if you keep a certain temperature for a very long time, what happens to a certain reaction, because some reactions will only take place at a certain temperature, but they might take place, what happens to them if you do it, that maintain that certain temperature for a very long time or not. So the final temperature is typically what you will maintain for at least 1 hour. You can maintain it for several hours as well. Okay. The PVC is one of the common graphite precursors, and for PVC there's another thing. PVC contains chloride. It's polyvinyl chloride, and chloride is no good. So we already learned that oxygen is not good, chloride is not good. But interestingly, we can remove this chloride from PVC in the form of hydrochloric acid. And that is typically done between 200 to 400 degrees. And that is done for several hours, which will basically form this hydrochloric acid, and the acid will be then removed. Around 300 something degrees also, this or below 400, the PVC also becomes liquid because it does degrade. But our goal is to make sure that most of the chlorine is removed, and after that, so the longer you do this process, more chlorine you can get rid of. And after that, the material that you actually get is very similar to the coke, the needle coke that we were talking about. So if you do this heat treatment, so you do this up to 400 degrees, you get rid of the HCl, and then maybe you also heat it a little bit more, and what you get is coke-like material, which can then be processed in a similar way that we processed coke. If you want to make certain shapes out of it, and then you can heat it up to 3000 degrees in order to graphitize it, or in order to get the graphite. Now over here you can see what happens at different temperature points. Why I'm always saying that we need to go to 3000 degrees. So this, you see, this is a cross section of a graphite crystal. So if you see the top one where you have 3000 degrees, that is a crystal which is your side view. So you saw these TEM images. These are the crystal planes. This is a cross section. Okay. Now if you go a little bit down, in terms of temperature, around 2000 degrees, what you see is little randomness. So it is still not perfect graphite crystallite. You go a little bit, to even lower temperatures, above 1000 degrees, 1000, 1100, 1200. Then you have the crystallites start to form, but they are still, now their LA, the length is length in A direction. Now the crystallite diameter, that's also much smaller. And of course, before that, the material is practically disordered. This is the reason that you need to go for higher temperatures when you want to get good crystals of graphite. Otherwise, also, let's say if you stop your process at 2000, what you have is then graphitic material. You can say highly graphitic material. Highly is basically also a relative term. So compared to what you have at 1000 degrees, you can say the 2000 degrees material is highly graphitic compared to what you have. But you can always improve the graphitic content, and at around 3000 degrees you can get a good graphite crystal, and that is why we go to those temperatures. However, this is not valid for all the polymers. Right now we are talking specifically about PVC. Now in this context, there is one more term that you need to understand very well, and it is known as pyrolysis. So this entire process where you are performing a heat treatment under an inert atmosphere, what do you call it, and what are the various stages of this process? So let's try to understand what is happening chemically. And now this is a more general form. I'm talking about various different polymers. Because most of the polymers, these are organic materials, so they are, what are they made of? They are made of carbon, hydrogen, nitrogen, oxygen, sulfur sometimes, and some other elements possible. But the primary components will always be carbon, hydrogen, nitrogen, and oxygen. Okay, so some of the reactions will remain common. Some of the bond breaking temperatures will remain common. because there is a certain strength, for example, of carbon-oxygen bond. Now, depending upon your polymer, you may go a little bit above or a little bit below the temperature, but depending upon the energy of your bond, it will not differ too much, because that is the energy of the carbon-oxygen bond or carbon-hydrogen bond, or carbon-hydrogen bond in the case of aromatic structure, ring-like structure, or aliphatic structure. You may sometimes also have some catalytic elements inside. So based on all of these things, let's define some very fundamental rules for all the polymers. So not just for PVC. Okay, what happens up to 200 degrees? You have a polymer, you may have some water in it, you may have some very standard volatile impurities. Those things will go away up to, let's say, 200 to 50, and yeah, nothing really chemically changed in most cases, depending of course upon your the degradation of your degradation temperature of your polymer. Okay, now interesting things start to happen. The carbon-oxygen bond cleavage takes place above 250. So this is a range, 250 to 350 degrees centigrade. So that will depend upon the exact chemical structure. But as I said, that let's define some general rules. Then what happens? You have carbon-nitrogen bonds breaking after that. Nitrogen does some interesting things, and that's why I've written 300 to 500. So there is a larger range for nitrogen also, because nitrogen sometimes serves as a chemical catalyst, which actually helps in forming aromatic structures, even though the material may not have aromatic structures to begin with. Okay, but then you have the carbon nitrogen bonds breaking. The last one to break is carbon-hydrogen. Why last? Because it's single bond. It's a stronger one, especially in the case of aromatic structures. This is the one which is the strongest, and that is removed at the end, or that is cleaved. So this is between 500 and 700 degrees for most polymers. There may be some exceptional cases here, which will only, they might not have complete degradation even up to very high temperatures, but for most polymers, this is what works. So up to 700 degrees, you will have most of the hydrogen bonds breaking, which means that your polymer will break into smaller and smaller and smaller fragments. Some of these smaller fragments, without further individual bond breaking, they will just leave your material, and they will because you have this nitrogen pushing them anyway. So sometimes as soon as they form a smaller hydrocarbon, they are out. And so on. But whatever is left, in most cases around 700 degrees, you will have pretty much a not a complete decomposition, but a very almost complete decomposition of your polymer, and most of the non-carbon atoms are now ready to leave or have already left. Okay, now when the non-carbon atoms leave, so my carbon and hydrogen had a bond, now hydrogen just went outside in some form. Now what happens to this carbon? This carbon is a radical now. It has an unpaired electron. The electron which was previously participating in bonding. Depends upon the, polymers can have sp2, sp3, all kinds of bonding. So whatever was the bonding, but there was that polymer was bound, that carbon atom was bonded to one or more other atoms. Now it is just a radical, which means it is ready to form a bond. Now that there is also another carbon atom who is a radical, and there are millions of these carbon atoms which are actually ready to form bonds. And what will carbon do in this case? Carbon is already happy forming bonds with itself. So all of these carbon atoms will then try to come together, and then they will form a large scale carbon material. Okay. This happens between, so this is what you will call the formation of carbon bonds, which goes on between 700 to 2000 degrees. It happens. It's because bonds can also rearrange themselves, and then there may be some high energy bonds, 9-membered rings. I don't know. There may be some high energy structures which will then try to get the lower energy state. So the bond rearrangements will continue to happen up to 2000 degrees. Okay. Now even also between the 700 and 2000 degree, between especially after 900 degrees typically, you will also have this because of the rearrangement of bonds, what you get is more and more graphitic content. What does that mean? That means your La and Lc, crystallite diameter, and the stack thickness both continue to increase as you provide more and more heat. Okay, so this, in the case of graphite, when your LaLc increase, they will have anisotropic crystals. But in the case of other carbons, they will increase, but they will still have very random orientation, and altogether in bulk your material will still be disordered. That we will discuss in the next section, but these are the general rules. This is what chemically takes place. Now about the names. Whatever happens in the first 4 steps or up to 700 degrees, that is what we call pyrolysis. Actually, to be more specific, whatever happens when the bond breaking first starts. So water removal, the first 100 degrees we don't count, but let's say whatever happens up to 700 degrees, in general, that is known as pyrolysis. This process of breaking of bonds of carbon and heteroatoms in the absence of oxygen. So this is purely thermal. Then it is called pyrolysis. Okay, this up to 2000 degrees, what happens, we call it carbonization, and then above 2000 degrees, typically what is called, it is known as the graphitization. Okay, so now this entire process, you can always call it heat treatment. Even if you just the pyrolysis part, if you call it heat treatment, it's not wrong, because it's always you are doing the heat treatment. What happens is, as such, we should call this entire process of converting polymer to carbon into heat treatment, but people often end up calling it just pyrolysis or just carbonization or just graphitization, because whatever is the most important reaction, whatever is the most important process that people are what they are aiming at, then they call it that. So pyrolysis is also, you can say that the polymer was converted into carbon via pyrolysis. So via pyrolysis means this happened. Or when you convert something into graphite, in order to show that you actually went all the way to 3000 degrees, you will just say that I have graphitized a carbon. So sometimes people will use one of these 3 terms, but you can always use the term heat treatment altogether. Okay. Yeah, so since the first step is pyrolysis, often people end up, and also a larger portion of it is pyrolysis, people often end up or calling it pyrolysis. One more reason for that is that during pyrolysis, you can actually make a lot of changes also. So if you can, for example, at a certain temperature, you see that your polymer has a lot of oxygen in it, for example. So you want to get rid of all of that. So you know that this is the window where I have oxygen leaving the material. You may keep your material for a very long time at that temperature in order to get rid of most of the oxygen. So this is where you basically play with the parameters. Also, you can increase the heating rate, decrease the heating rate. So all of these things are done during pyrolysis, and that is why often people call this entire heat treatment just pyrolysis. Okay. Yeah, so these were the general rules. The exact conditions, which include the exact pyrolysis temperatures, or the temperature of each step for that matter, that will be slightly vary depending upon the chemical structure of the polymers. Okay. This is a very complex reaction. What you have from pyrolysis, this pyrolyzing matrix. Pyrolyzing matrix means a mixture of all the multiple things. You have some, for example, I take 600 degrees. I choose any temperature point. What do you have in your material at that point? You have some fragmented hydrocarbons, so bigger hydrocarbons, smaller hydrocarbons, some parts of your polymer still left over. You may have some bubbles forming because you have some gaseous things that are going out, that are the volatile hydrocarbons. You may also have each of these smaller hydrocarbons breaking into further hydrocarbons. You have also some carbon atoms, maybe some carbon radicals have already formed carbon-carbon bonds, so you may have some solid carbon also at that point. So at any given point, this crazy mixture of material will be called pyrolyzing matrix. And these reactions for any pyrolysis of any polymer can be extremely complex to understand, because you have so many different reactions that are going on. Okay, now I mentioned it before that when we have smaller structures, because we have a higher surface to volume ratio, we can sometimes use lower pyrolysis temperatures. This is something we are going to learn when we learn about micro nano fabrication.